Hello and welcome to the Snoozy Scientist. I'm very glad you found your way here. Before we settle into tonight's topic, I'd love to know where in the world you're listening from. Maybe you're tucked into bed after a long day, stretched out on the sofa, travelling somewhere late at night, or simply looking for something calm to listen to while the rest of the world quietens down. Wherever you happen to be, I hope you can get comfortable and enjoy the next little while. And because the Snoozy Scientist is a very new channel, if you enjoy these slower, sleepier journeys through science, leaving a like or subscribing is a wonderful way to help it find its feet and reach a few more curious night owls. And if you've already subscribed this early on, thank you. It genuinely means a great deal to have you here from the beginning. Tonight we're going to explore something that seems incredibly simple until you ask one awkward question about it. Everything around you has mass. Your bed has mass. The earth has mass. The atoms in your body have mass. But when we follow matter down into the quantum world, the answer to where that mass actually comes from becomes far stranger than simply finding smaller and smaller pieces. Some of it is connected to the Higgs field. Much of the mass in ordinary matter comes from something quite different, hidden inside protons and neutrons, where quarks and gluons are constantly interacting in ways that are anything but still. So let's begin, shall we? What is mass actually made of according to quantum physics? Mass seems like one of those ideas that should be almost embarrassingly simple. Pick up a stone and it has mass. Step onto a set of scales and you have mass. Look at a planet, a star, a grain of sand, or a cup of tea, and each of them has some measurable amount of mass. It feels so familiar that it is tempting to imagine mass as a kind of invisible substance packed inside everything, but that is not how modern physics describes it. Mass is a property of a physical system. It is something we can measure, compare, and use to predict how objects behave, but it is not a separate material ingredient hiding inside matter. There are no little grains of mass sitting inside a proton, waiting to be uncovered if we look closely enough, and that distinction turns out to be extremely important. It also helps to separate mass from several ideas that are often mixed together in everyday conversation. Mass is not the same thing as weight. Weight depends on gravity. If you travelled from Earth to the Moon, your mass would remain essentially unchanged, but your weight would fall to roughly 1/6 of its value on Earth because the Moon's surface gravity is much weaker. Mass is not the same as size either. A huge cloud can occupy an enormous volume while containing far less mass than a comparatively small mountain. Nor is mass the same as density. Density describes how much mass is contained within a particular volume, which is why a small block of a very dense material can contain more mass than a much larger object made from something light and porous. Even the familiar phrase amount of matter can be slightly misleading. It works reasonably well in ordinary life, but modern physics eventually forces us to be more careful, because the mass of a composite object is not always obtained by simply adding together the rest masses of the particles inside it. Classical physics approached mass in a more straightforward way. Isaac Newton treated mass as one of the fundamental properties of an object. In Newtonian mechanics, mass measures how strongly an object resists acceleration. Push gently on an empty shopping trolley and it responds quite easily. Load the same trolley with something heavy and the same push produces less acceleration. This idea is called inertial mass. Newton's second law expresses the relationship between force, mass, and acceleration. Written in words, it says that force equals mass multiplied by acceleration. The greater the mass, the more force is required to produce the same acceleration. There is also gravitational mass, which describes how an object participates in gravity. Remarkably, experiments show that inertial mass and gravitational mass behave as though they are equivalent. Albert Einstein later made this equivalence central to his general theory of relativity. But even before gravity enters the story, Einstein had already changed the meaning of mass in a profound way. In special relativity, mass is connected with energy and momentum. The modern quantity physicists usually mean when discussing the mass of a particle or isolated system is invariant mass, sometimes informally called rest mass. It does not depend on which inertial observer is measuring it. Energy and momentum can change from one observer to another. Invariant mass does not. The relativistic relationship can be expressed in words as energy squared equals momentum times the speed of light, all squared, plus mass times the speed of light squared, all squared. That relationship contains something deeply important. A system can have mass because of the total energy contained within it, even when some of its individual constituents have no rest mass at all. Conversely, the mass of a bound system does not always equal the simple sum of the masses of its parts. This is where the everyday picture begins to fail. Imagine asking what a kilogram is made of. At first it seems reasonable to keep dividing the object into smaller pieces. Molecules become atoms. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons. It might seem that eventually we should arrive at tiny objects that possess little packets of mass, and that all we need to do is add those packets together. Quantum physics gives us a much stranger answer. The mass of ordinary matter comes from several different physical mechanisms. Some elementary particles have intrinsic masses connected with their interactions with the Higgs field, but most of the mass in the familiar matter around us does not come directly from adding those elementary particle masses together. Nearly all the mass of an ordinary atom is concentrated in its nucleus. Electrons are extraordinarily light by comparison. A proton is roughly 1,836 times as massive as an electron, and neutrons are slightly heavier than protons. So if you are sitting in a chair, lying in bed, or holding a mug in your hand, almost all of the ordinary matter mass involved is associated with protons and neutrons. And this creates a fascinating problem. The quarks inside those protons and neutrons have intrinsic masses that account for only a small fraction of the final mass of the particles they form. Most of the rest comes from the energy of an intensely active quantum system involving quarks, gluons, motion, fields, and the strong interaction. So the question of what mass is made of already needs a small correction. Mass is not really made of anything in the way a wall is made of bricks. It is a property of particles and systems connected with their energy, momentum, interactions, and quantum fields. And for most of the ordinary matter we see around us, understanding mass means looking not merely at what matter contains, but at what those quantum ingredients are doing. The idea that mass can emerge from energy becomes much easier to understand once we leave behind the older picture of mass as something simply attached to an object from the beginning. In 1905, Albert Einstein published his special theory of relativity, and one of its most famous consequences was the relationship between mass and energy. In its simplest form, for an object at rest, energy equals mass multiplied by the speed of light multiplied by the speed of light. This is often shortened in conversation to the claim that mass is energy. That is useful as a first hint, but it can also be misleading. Mass and energy are not two substances that can simply be swapped around like different currencies. Mass is a property of a particle or physical system, while energy is a quantity that can take many forms. The important point is that the energy contained within a system affects the mass of that complete system. To see why, It helps to distinguish rest energy from kinetic energy. An object sitting still relative to you possesses rest energy simply because it has mass. If it begins moving, it also gains kinetic energy. Older descriptions sometimes say that the object's mass increases as it moves faster, but modern physics usually avoids talking about relativistic mass in this way. Instead, the object's invariant mass stays the same. Its energy increases. Its momentum increases, but its fundamental rest mass does not simply swell because it happens to be travelling quickly past you. This distinction became especially clear through the work of Hermann Minkowski, who showed that special relativity could be understood geometrically by treating space and time as parts of a single four-dimensional structure called spacetime. Different observers moving relative to one another may disagree about an object's energy and momentum, yet they can still calculate the same invariant mass. The complete relationship can be spoken as energy squared equals momentum multiplied by the speed of light, with that entire quantity squared, plus mass multiplied by the speed of light squared, with that entire quantity squared. It may sound a little less elegant when said aloud than when written on a blackboard, but hidden inside it is a remarkably useful idea. Consider a photon. A photon is a quantum of electromagnetic radiation. It can carry energy. It can carry momentum. Sunlight can push gently against objects, and photons transferring momentum are part of the reason solar sails can, in principle, propel spacecraft. Yet a photon has zero invariant rest mass. That is perfectly consistent with relativity, because the photon's energy is associated with its momentum. Mass is not required for something to possess energy. Now imagine something slightly stranger. Suppose we have several particles moving around inside a closed system. Each particle has its own energy and momentum. If we examine the complete system from a frame in which its total momentum is zero, the total energy remaining in that system determines its invariant mass. This means that internal motion can contribute to mass. A box containing energetic particles can therefore have more mass than an otherwise identical empty box. The particles do not need to acquire larger individual rest masses. Their energy is simply part of the total energy of the complete system. Even radiation can do this. If light is trapped inside a perfectly reflecting container, the container with the light inside has very slightly more mass than the same container without it. Nothing mysterious has been sprinkled into the box, it simply contains more energy. But the effect can also work in the opposite direction. When particles attract one another and settle into a stable bound state, energy may be released. Once that energy has escaped, the finished bound system can weigh slightly less than the separated components did beforehand. This missing mass is associated with binding energy. A familiar example appears inside atomic nuclei. When protons and neutrons form a tightly bound nucleus, the mass of that nucleus can be lower than the combined masses of the same protons and neutrons when separated. The difference is small, but absolutely real. So relativity gives us a much more flexible picture of mass than the simple idea of adding together the masses of microscopic ingredients. And this becomes extremely important in quantum physics. A proton, for example, contains quarks. Those quarks possess intrinsic masses of their own, but adding those masses together produces only a small fraction of the proton's measured mass. The rest is connected with the energy of the quantum system itself. The quarks are moving. Gluon fields are present. Strong interactions store and redistribute energy. All of this contributes to the total rest energy of the proton, and therefore to its invariant mass. This also reveals why there is no single answer to the question of where every bit of mass comes from. An elementary particle such as an electron has an intrinsic mass associated with its interaction with the Higgs field. A composite object such as a proton can possess a much larger mass because of the total energy contained in its interacting quantum fields. A bound nucleus can then have a slightly smaller mass than the separate protons and neutrons from which it formed. Mass, in other words, is not assigned to everything by one universal microscopic process. Sometimes it belongs to an elementary particle. Sometimes it emerges from the energy of a complicated system. And once matter is viewed through both relativity and quantum physics, the mass of an object begins to look less like the amount of some hidden substance inside it, and more like a quiet accounting of all the energy held within the system as a whole. If we keep following matter downward, past atoms and into the particles inside them, there comes a point where the familiar idea of tiny objects becomes less and less useful. It is natural to picture an electron as an incredibly small bead, or a quark as an even smaller speck tucked somewhere inside a proton. That picture can be helpful at first, but modern quantum physics describes something more subtle. At the deepest level available in our best current theories, nature is described in terms of quantum fields. A field is something that has a value throughout space. The idea is not unique to quantum physics. A magnetic field can extend through a region even when nothing obvious appears to occupy it. A gravitational field can influence an object across empty space. Quantum field theory takes this idea much further. According to quantum field theory, every known type of elementary particle is associated with a corresponding quantum field extending throughout the universe. There is an electron field, there are several quark fields, there is an electromagnetic field, there are gluon fields associated with the strong interaction, fields associated with the weak interaction, and the Higgs field. An electron in this description is not simply a tiny solid object sitting inside the electron field, it is a quantist excitation of that field. A useful comparison is a wave travelling across the surface of water, although the comparison should not be taken too literally. The wave is not a separate substance added to the water, it is a particular excitation of the water itself. Quantum fields behave according to very different rules, but the basic lesson is useful. What we call a particle can be understood as a distinct excitation of an underlying field. One of the major historical steps toward this picture came from Paul Adrien Maurice Dirac. During the late 1920s, Dirac developed a relativistic quantum description of the electron. Earlier quantum mechanics had already transformed ideas about atoms, but combining quantum theory with Albert Einstein's special relativity created serious difficulties. Dirac found an equation that successfully described electrons while respecting special relativity, and the mathematics contained a surprise. It allowed solutions that eventually led Dirac to predict a particle with the same mass as the electron, but opposite electric charge. This particle, the positron, was discovered experimentally by Carl David Anderson in 1932. Antimatter had emerged from the attempt to make quantum mechanics and relativity work together. Developments like this helped lead toward quantum field theory, where particles can be created and destroyed rather than existing as an eternally fixed collection of objects. The modern framework built from these ideas is called the Standard Model of Particle Physics. The Standard Model describes the known elementary particles and 3 of the 4 fundamental interactions. Matter particles are divided into quarks and leptons. Electrons belong to the lepton family. Quarks occur in 6 varieties called up, down, charm, strange, top, and bottom. Other particles act as carriers of interactions. Photons are associated with electromagnetism. Gluons are associated with the strong interaction. W bosons and Z bosons are associated with the weak interaction. The Higgs field and its particle excitation, the Higgs boson, occupy a particularly important place because interactions with the Higgs field are connected with the masses of several elementary particles. Gravity is the major omission. The standard model does not contain a complete quantum description of gravity. Gravitation is instead described extremely successfully on large scales by Albert Einstein's general theory of relativity. Combining gravity consistently with quantum physics remains one of the great unfinished problems in fundamental physics. For the particles that make ordinary matter, however, the standard model works extraordinarily well, and it introduces an important distinction. Some particles are elementary, meaning that no smaller internal components have been experimentally established within them. The electron is treated as elementary. So are quarks. A proton is different. A proton is a composite quantum system containing quark and gluon fields. A neutron is composite as well. This means that asking where an electron gets its mass and asking where a proton gets its mass are not quite the same question. The electron has an intrinsic mass associated with the electron field and its interaction with the Higgs field. The proton's mass includes the effects of the quarks inside it, but most of its measured mass emerges from the energy of the strongly interacting quantum system formed by quarks and gluons. Even empty space looks different in this framework. In quantum field theory, the vacuum does not mean that every field has vanished. Instead, the vacuum is the lowest energy state of the quantum fields. The fields are still part of the description of nature even when no ordinary particles are present. This becomes especially important for the Higgs field because its lowest energy state has a non-zero value. Empty space therefore does not correspond to the Higgs field simply being absent. Every excitation of a quantum field also comes with characteristic properties. An electron has electric charge, spin, and mass. Quarks have electric charge, spin, mass, and color charge associated with the strong interaction. Photons have spin and energy, but zero rest mass. Mass is therefore one property describing how a particular excitation behaves. It influences the relationship between energy and momentum and determines, among other things, whether an isolated particle can possess a rest frame. A massive particle can, in principle, be observed in a frame where its momentum is zero. A photon cannot. In empty space, it always moves at the speed of light. So beneath the apparently solid world of tables, stones, planets, and people lies a very different description. Quantum fields extend through space. Their excitations appear to us as particles. Those excitations interact, combine, exchange energy, and sometimes form larger structures whose properties cannot be understood simply by adding together the properties of their individual ingredients. And mass sits right in the middle of this picture. For elementary particles, it can be tied to the behavior of the underlying fields themselves. For composite particles such as protons and neutrons, it can emerge largely from the energy created by interactions among those fields. The universe, in this modern description, is not fundamentally a collection of tiny pieces of matter sitting in empty space. It is a universe of quantum fields, and what we call particles are some of the things those fields can do. Once physicists began describing nature in terms of quantum fields, mass became more than a number that could simply be attached to a particle whenever it was needed. The reason was symmetry. Symmetry in physics does not always mean that something looks the same when reflected in a mirror or rotated. In quantum field theory, symmetry can describe mathematical transformations that leave the measurable predictions of a theory unchanged. A particularly important kind is called gauge symmetry. Gauge symmetry is built deeply into the modern descriptions of the fundamental forces. It tells physicists that certain changes in the mathematical description of a field do not represent genuine changes in the physical world. Different descriptions can therefore represent exactly the same observable situation. This may sound rather abstract, but these symmetries do something extremely useful. They strongly restrict which interactions are allowed and help produce quantum theories that remain mathematically consistent when particles interact at very high energies. The difficulty was that mass did not always fit comfortably into this elegant framework. During the 20th century, physicists discovered that electromagnetism and the weak nuclear interaction could be described as different aspects of a deeper theory. Sheldon Lee Glashow, Abdus Salam, and Steven Weinberg played central roles in developing what became known as electroweak theory. Electromagnetism is carried by photons. The photon has no rest mass, which is closely connected with the enormous range of the electromagnetic force. Light can cross galaxies because photons do not need to decay away after travelling a short distance. The weak interaction behaves very differently. It is involved in processes such as radioactive beta decay and in reactions that take place inside stars. Its range is extraordinarily short, extending only across distances much smaller than an atomic nucleus. The particles responsible for transmitting the weak interaction are the charged particles called the W bosons and the neutral particle called the Z boson. Unlike photons, these particles are extremely massive. The W bosons have masses corresponding to energies of roughly 80 billion electron volts, while the Z boson is a little heavier at roughly 91 billion electron volts. A proton, by comparison, has a mass corresponding to less than 1 billion electron volts, so the particles carrying the weak interaction are extraordinarily heavy by subatomic standards, and this created an awkward theoretical question. Electroweak theory placed the electromagnetic and weak interactions within the same mathematical structure. Yet one part of the theory involved a massless photon, while another involved very massive weak bosons. One might imagine solving the problem by simply writing the required masses into the equations. Unfortunately, it was not that easy. Adding ordinary explicit mass terms for the weak gauge bosons would spoil the gauge structure that made the theory work. The mathematical consistency of the quantum theory depended on preserving this symmetry in the underlying equations. Physicists therefore faced an unusual situation. Experiment demanded massive weak particles, while the most successful mathematical framework for describing their interactions resisted simply giving them masses directly. The solution required a new idea. That idea was spontaneous symmetry breaking. Despite the name, spontaneous symmetry breaking does not mean that a physical object suddenly cracks into an asymmetrical shape. It describes a situation in which the fundamental laws possess a symmetry, but the lowest energy state of the system does not display that symmetry in the same obvious way. A simple analogy comes from balancing something perfectly upright. The rules may treat every direction equally, yet once the object falls, it settles in one particular direction. The laws have not changed, but the state that the system occupies no longer looks equally balanced in every direction. Quantum fields can behave in an analogous, although much more mathematical, way. In electroweak theory, the crucial issue is the state of the fields filling empty space. What physicists call the vacuum is the lowest energy state available to those quantum fields. If this vacuum had the same obvious electroweak symmetry as the underlying equations, the weak gauge bosons would remain massless in the straightforward version of the theory. But nature appears to choose a different kind of lowest energy state. The underlying electroweak theory retains its gauge structure, while the vacuum state is arranged in a way that distinguishes the electromagnetic interaction from the weak interaction. This is where the Higgs field enters. Its presence allows the electroweak symmetry to be hidden in the vacuum while preserving the deeper mathematical consistency of the theory. Through this mechanism, the W and Z bosons behave as massive particles while the photon remains massless. It is one of the most elegant pieces of the Standard Model. But it is also important not to let the story become too neat. Solving the electroweak mass problem does not mean that physicists have explained every kind of mass using one universal mechanism. The Higgs field is essential for understanding the intrinsic masses of several elementary particles, yet most of the mass contained in ordinary objects is concentrated in protons and neutrons, and most of their mass comes from the energy of the strong interaction rather than directly from the Higgs field. So the original mass problem of electroweak theory led physicists toward the Higgs mechanism, but the deeper question of why the matter around us is heavy still has another, very different quantum story hidden inside it. The Higgs field is often described as though it was some invisible substance spread through the universe, quietly surrounding every particle and somehow making it heavy. That picture is memorable, but the real idea is both stranger and more precise. During the 1960s, several physicists were investigating how spontaneous symmetry breaking could work inside relativistic quantum field theories. Robert Brute and Francois Englert published one important treatment. Peter Higgs independently developed a closely related idea, and Gerald Guralnik, Carl Richard Hagen, and Thomas Walter Bannerman Kibble produced another influential formulation. Their work showed that a quantum field could have a non-zero value throughout empty space, and through its interactions with other fields, allow particles associated with a gauge theory to behave as though they possessed mass. The field involved in the Standard Model is now known as the Higgs field. Like the electron field or electromagnetic field, the Higgs field is treated as fundamental. It is not thought to be made from some smaller known substance, and according to the Standard Model, it extends throughout space. The unusual part concerns what happens even when space contains no ordinary particles. In quantum field theory, empty space is described by the vacuum state, meaning the lowest energy state available to the fields. For many familiar fields, it is reasonable at an introductory level to imagine the vacuum as corresponding to no ordinary field excitation being present. The Higgs field behaves differently. Its lowest energy state occurs when the field has a non-zero value. In other words, removing particles from a region of space does not make the Higgs field disappear or settle at zero. Even the vacuum possesses a Higgs field value. This is called the vacuum expectation value of the Higgs field. Its characteristic scale is roughly 246 billion electron volts. That number does not mean that every patch of empty space contains a little reservoir weighing 246 billion electron volts in the ordinary sense. It describes the scale associated with the Higgs field's non-zero vacuum value and its role in electroweak physics. The existence of this background changes the behavior of other quantum fields. Before electroweak symmetry breaking is considered, the mathematical description treats the electromagnetic and weak interactions as parts of a common electroweak structure. Once the Higgs field settles into its non-zero vacuum state, the fields associated with these interactions behave differently. The particles associated with the weak interaction become massive, while the photon remains massless. This is the heart of the Higgs mechanism. There is, however, a popular analogy that needs some gentle repair. The Higgs field is sometimes compared with a thick syrup, with particles becoming massive because they have difficulty moving through it. Another version imagines an important person walking through a crowded room, attracting people around them and therefore becoming harder to move. These pictures can provide a vague sense that different particles interact differently with the Higgs field, but they can also create the wrong impression. The Higgs field does not behave like friction. A massive electron travelling through empty space is not continually losing energy because the Higgs field is dragging against it. It is not being slowed down by a cosmic treacle that fills the universe. If that were happening, particles moving through empty space would steadily dissipate energy, which is not what the Higgs mechanism predicts. Instead, the interaction changes the fundamental relationship between energy and momentum for the excitation of a particular field. A particle with mass requires energy even when viewed in a frame where its momentum is zero. That rest energy is part of what it means for the corresponding quantum excitation to be massive. For the elementary fermions of the Standard Model, including electrons and quarks, interactions with the non-zero Higgs field establish their intrinsic masses. Different particles interact with the Higgs field by different strengths, which is why their masses can differ so dramatically. There is another distinction worth keeping clear. The Higgs field is not the same thing as the Higgs boson. The field is the underlying quantum field extending throughout space and possessing a non-zero vacuum value. The Higgs boson is an excitation of that field. A loose comparison might be the difference between the surface of a lake and a ripple travelling across it. The lake can be present without a particular ripple. In a similar conceptual sense, the Higgs field existed as part of the theory long before anyone produced and detected a Higgs boson experimentally. The Higgs boson represents a disturbance around the field's vacuum state. This distinction matters because the phrase that the Higgs boson gives particles mass is not quite right. The mechanism involves interactions with the Higgs field. The boson is evidence of the field's dynamics, not a tiny object travelling around handing out mass to passing particles. There is an even larger misconception hiding nearby. It is often said that the Higgs field gives everything its mass. That statement is only partly true. The Higgs field is essential for the intrinsic masses of elementary particles such as electrons and quarks, and it is essential to the masses of the weak interactions massive gauge bosons. But a human body is not heavy, mainly because the Higgs field directly gives enormous masses to the quarks inside it. Most of the mass of ordinary matter is concentrated in protons and neutrons. The intrinsic masses of the light quarks inside those particles contribute only a relatively small part of their total mass. Most of the remainder emerges from the energy associated with the strong interaction, including the motion and interactions of quarks and gluons. So the Higgs field is tremendously important, but its role is more specific than the popular slogan suggests. Without it, the known structure of elementary particle masses and the electroweak interaction would be radically different. But if we want to understand why a stone, a planet, or a human body has almost all of the mass that it does, the Higgs field is only one part of the answer. A much larger contribution is waiting inside the quantum structure of protons and neutrons. The Higgs field becomes especially important when we look closely at the weak interaction, because this is where the mechanism was originally needed most urgently. Electromagnetism and the weak interaction are described together by electroweak theory. At sufficiently high energies, they appear as parts of one deeper framework. Yet at the energies we encounter in ordinary life, the two forces behave very differently. Electromagnetism has an unlimited range. Light can cross enormous stretches of space, and the electromagnetic influence of a charged particle weakens with distance, but does not suddenly disappear after some fixed boundary. The weak interaction is different. Its effective range is extraordinarily short, much smaller than the diameter of an atomic nucleus. The reason is closely connected with the particles that carry these interactions. Electromagnetism is associated with the photon, which has zero rest mass. The weak interaction is associated with three massive gauge bosons. Two are electrically charged and are called the positively charged W boson and the negatively charged W boson. The third is electrically neutral and is called the Z boson. These particles are remarkably heavy by the standards of particle physics. The W bosons have masses corresponding to roughly 80 billion electron volts. The Z boson is heavier still, at roughly 91 billion electron volts. For comparison, a proton has a mass corresponding to a little under 1 billion electron volts. So a single weak boson has a mass dozens of times greater than that of a proton. Their large masses are directly connected with the tiny range of the weak interaction. Very loosely speaking, transmitting an interaction through such massive quantum fields is fundamentally different from transmitting electromagnetism through the massless photon field. The enormous masses of the weak bosons limit the distances across which weak processes are significant, but these masses could not simply be inserted into electroweak theory by hand without creating serious mathematical problems. This is where the Higgs field changes the situation. The Higgs field has a non-zero value even in the vacuum. Its characteristic vacuum scale is roughly 246 billion electron volts. That number describes the scale of electroweak symmetry breaking. It should not be imagined as though every portion of empty space contains an ordinary lump of matter weighing 246 billion electron volts. It is a property of the Higgs field and the vacuum state of the electroweak theory. When the Higgs field settles into this non-zero vacuum state, it interacts with the gauge fields involved in the electroweak interaction. The result is that particular combinations of those fields behave as massive particles. Those combinations become the W bosons and the Z boson. Another combination becomes the photon, and the photon remains massless. This detail is extremely important because the Higgs mechanism does not simply move through the standard model giving mass to every particle it encounters. Its effect depends on the structure of the underlying theory and on how particular fields interact with the Higgs field. After electroweak symmetry breaking, an unbroken electromagnetic gauge symmetry remains. Because that symmetry survives, the photon associated with electromagnetism remains exactly massless within the standard model. So we end up with a rather elegant result. Electromagnetism and the weak interaction begin as parts of a shared electroweak framework. Yet after the Higgs field takes on its vacuum value, the particles associated with the weak interaction become massive, while the photon does not. There is an additional way of understanding what has happened. A massless gauge boson has two physical polarization states. A massive spin 1 particle requires an additional state corresponding, loosely speaking, to motion or polarization along its direction of travel. That extra state has to come from somewhere. During electroweak symmetry breaking, components associated with the Higgs field become incorporated into the massive W and Z bosons. Physicists sometimes describe these components as being absorbed or eaten by the gauge bosons. The language is memorable, although fortunately no actual subatomic dining takes place. These components provide the additional longitudinal degrees of freedom required for the weak bosons to behave as massive spin 1 particles. One physical Higgs degree of freedom remains behind, and excitations of that remaining field appear as the Higgs boson. This is one reason the Higgs mechanism is such an elegant construction. It allows the weak bosons to acquire mass while preserving the deeper gauge structure needed for the quantum theory to remain consistent. It is also useful to compare the photon with another set of massless particles. Gluons, which carry the strong interaction, also have zero rest mass. but they remain massless for a different structural reason. Gluons belong to quantum chromodynamics, the separate gauge theory describing the strong interaction. They do not acquire mass through electroweak symmetry breaking. This creates an interesting collection of possibilities within the same standard model. The photon is massless. The gluons are massless. The W and Z bosons are extremely massive. And all of these particles are gauge bosons associated with fundamental interactions. So the Higgs mechanism is not a universal rule saying that every quantum field must become heavy. It is a specific consequence of how the Higgs field interacts with the electroweak sector. This matters because discussions of ordinary matter can sometimes make the Higgs field sound less important than it really is. It is true that most of the mass in protons and neutrons does not come directly from the Higgs mechanism. Most of that mass emerges from strong interaction dynamics involving quarks and gluons. But this does not make the Higgs mechanism a minor detail. Without it, the W and Z bosons would not possess their observed masses within the standard model. The weak interaction would behave very differently, and many of the processes involved in radioactive decay, stellar nuclear reactions, and the evolution of matter would be altered profoundly. The weak bosons therefore provide one of the clearest examples of mass arising directly through interaction with the Higgs field. They also reveal something important about mass more generally. Different particles can be massless or massive for very different reasons. Even within one quantum theory, there is no single microscopic story that applies equally to everything. And that becomes even clearer when we turn from the gauge bosons carrying forces to the elementary particles that make up matter itself. Because electrons and quarks acquire their intrinsic masses through another kind of interaction with the same Higgs field. The Higgs field does more than help the weak bosons become massive. It also plays a central role in explaining why familiar elementary particles, such as electrons and quarks, possess intrinsic mass at all. The mechanism is not quite the same as the one that gives mass to the W and Z bosons. Electrons and quarks belong to a class of particles called fermions. Within the standard model, their masses arise through interactions with the Higgs field known as Yukawa interactions. The name comes from Hideki Yukawa, although the specific Yukawa interactions involving the Higgs field are part of the later electroweak theory rather than Yukawa's original theory of the nuclear force. The important idea is fairly simple. Different fermion fields interact with the Higgs field with different strengths. That strength is described by a number called a Yukawa coupling. Once the Higgs field settles into its non-zero vacuum value, these interactions appear to us as the masses of the fermions. A stronger Yukawa coupling produces a larger mass. A weaker coupling produces a smaller one. So an electron is light, not because there is only a small amount of Higgs field around it. The Higgs field has the same vacuum value throughout ordinary empty space. The difference lies in how strongly the electron field interacts with that background. Quarks follow the same broad principle. The up quark field has one coupling strength, the down quark field has another. The strange, charm, bottom and top quark fields each have their own. The result is an extraordinary range of elementary particle masses. An electron has a rest energy corresponding to roughly 500,000 electron volts. The top quark, by contrast, has a mass corresponding to roughly 173 billion electron volts. That makes the top quark more than 300,000 times heavier than the electron. Yet both fit within the same general Higgs framework. The Higgs field does not decide that one particle should be large and another small through some visible mechanical process. The difference is encoded in the strengths of their Yukawa interactions. And here we reach one of the standard model's unresolved questions. The theory contains these coupling strengths as measured parameters. It tells us how particle masses arise once those couplings are specified, but it does not explain from first principles why the electron has precisely its observed coupling, why the top quark interacts so much more strongly, or why the entire family of quarks and leptons has the peculiar pattern of masses that experiments reveal. Physics can describe the mechanism extremely well without yet explaining why nature chose these particular numbers. This is an important distinction between explaining how something happens and explaining why its numerical value is what it is. The electron provides a useful example. Its intrinsic mass is essential to the structure of ordinary matter. If the electron mass were radically different, atomic sizes, chemical energies, and the behavior of matter would all change. But the electron contributes surprisingly little to the total mass of an ordinary atom. A proton has a rest energy of roughly 938 million electron volts. That makes a proton approximately 1,836 times more massive than an electron. In a hydrogen atom, which contains one proton and one electron, almost all the mass therefore belongs to the proton. In heavier atoms, the dominance of the nucleus is even more obvious, because the nucleus contains many protons and neutrons, while the surrounding electrons remain comparatively light. At first, this might seem to strengthen the familiar statement that the Higgs field gives matter its mass. After all, protons are made partly from quarks, and quarks receive intrinsic masses through their Higgs interactions. But the numbers reveal something surprising. The proton contains 2 up valence quarks and 1 down valence quark. The intrinsic mass parameters of the up and down quarks are only a few million electron volts each when quoted at commonly used reference scales in particle physics. These values require some care because quark masses depend on the energy scale and mathematical convention used to define them. Quarks cannot be removed from a proton and placed individually on a scale. Even so, the basic comparison is unmistakable. Adding the intrinsic masses associated with the proton's light valence quarks gives only a small fraction of the proton's total mass of roughly 938 million electron volts. So most of the proton cannot simply be explained by saying that 3 quarks received mass from the Higgs field and were then placed together. Something much larger is happening inside. The quarks are confined within an intensely interacting quantum system. They move relativistically. Gluon fields carry energy. Quarks and gluons continually interact through the strong interaction. The proton's internal state is far more complicated than 3 tiny particles sitting quietly beside one another. All of that internal energy contributes to the proton's invariant mass. This is why the popular phrase that the Higgs gives particles mass needs to be handled carefully. For known massive elementary particles such as electrons and quarks, Higgs interactions are indeed central to their intrinsic masses. But most of the mass we encounter in ordinary visible matter belongs to composite particles, especially protons and neutrons, and their masses are dominated by something else. The Higgs field supplies the light quarks with their intrinsic mass parameters, and those masses are physically important. But when those quarks become part of a proton, the strong interaction creates a quantum system whose total mass is vastly greater than the simple sum of those quark masses. So the deeper mystery is no longer why quarks themselves possess mass. It is why a proton containing such light quarks ends up so much heavier than the ingredients seem to suggest. For decades, the Higgs field existed as a remarkably successful theoretical idea without anyone having directly observed the particle associated with it. That distinction matters. Physicists had built the Higgs field into the standard model because it provided a consistent explanation for electroweak symmetry breaking and for the masses of several elementary particles. The theory worked extremely well. But a theory can be elegant and useful without necessarily being the way nature actually behaves. There needed to be experimental evidence. Quantum field theory provided a way to look for it. If the Higgs field truly exists, then it should be possible to disturb that field and create a quantist excitation of it. That excitation is the Higgs boson. The Higgs boson is therefore not the Higgs field itself. It is a particle associated with a temporary excitation of the field, rather like a particular ripple revealing something about the medium capable of supporting it. Producing such a particle is not easy. The Higgs boson is extremely massive by elementary particle standards, with a mass corresponding to roughly 125 billion electron volts. Creating one, therefore, requires concentrating an enormous amount of energy into a very small region. That task eventually fell to the Large Hadron Collider at the European Organisation for Nuclear Research, near Geneva on the border between Switzerland and France. The Large Hadron Collider is a circular particle accelerator roughly 27 kilometers around. It accelerates beams of protons in opposite directions until they are traveling extremely close to the speed of light, then brings those beams together at selected collision points. The goal is not really to smash protons together simply for the drama of it. At sufficiently high collision energies, some of the energy involved can be transformed into new massive particles. Most collisions produce more familiar outcomes, but among an enormous number of events, a very small fraction can produce rare particles that exist only briefly. The Higgs boson was one of the most important targets. Two enormous experiments were designed to study the debris from these collisions independently. One was the Atoroidal Large Hadron Collider Apparatus experiment. The other was the Compact Muon Solenoid experiment. Each used layers of sophisticated detectors surrounding a collision point, allowing physicists to reconstruct the particles produced when high-energy proton collisions occurred. The Higgs boson itself does not survive long enough to travel calmly into a detector and announce its presence. Its lifetime is extraordinarily short. Almost as soon as it is created, it decays into other particles. Physicists therefore have to work backwards. They measure particles such as photons, electrons, muons, quarks, and weak bosons produced after collisions. They then examine the energies, momenta, directions, and combinations of those particles to determine whether some events are consistent with the decay of a heavier particle that existed only fleetingly. It is a little like identifying something by its footprints after it has already disappeared, except the footprints arrive in quantities measured across billions upon billions of particle collisions. Different Higgs bosons can decay through different channels. Some produce pairs of photons. Others ultimately produce combinations involving Z bosons or W bosons. The Higgs boson can also decay into matter particles, including bottom quarks and tau leptons. No single collision proves that a Higgs boson existed. Instead, physicists look for a statistical excess of events above the expected background produced by other known processes. As more data accumulate, a pattern can begin to emerge. On the 4th of July 2012, scientists at the European Organisation for Nuclear Research announced that both major experiments had independently found evidence for a new particle near 125 billion electron volts. The statistical significance had reached the level particle physicists traditionally require before describing a new effect as a discovery. Something new was there. But even then, careful physicists did not simply declare every question finished. Finding a new particle at approximately the expected mass was only the beginning. Researchers then had to determine whether its other properties matched those predicted for the standard model Higgs boson. One particularly important property was spin. The standard model Higgs boson is predicted to have spin 0, making it very unusual among known elementary particles. Measurements of its decay products supported this prediction. Its parity and other quantum characteristics were studied as well. Physicists also measured how often the particle was produced and how frequently it decayed into different combinations of particles. Over time, those measurements increasingly matched the expectations for the standard model Higgs boson. The new particle behaved as though it were indeed the quantum excitation associated with the Higgs field. This was an extraordinary confirmation of an idea developed nearly half a century earlier. But the discovery is sometimes described in a way that gives the Higgs boson rather more responsibility than it deserves. Headlines occasionally suggested that physicists had discovered the source of all mass. They had not. The discovery strongly confirmed the Higgs mechanism as part of the standard model and established the existence of a Higgs boson with the expected properties. That is a major achievement. It supports the explanation for why the W and Z bosons are massive, and why elementary fermions such as electrons and quarks possess intrinsic masses through their interactions with the Higgs field. But it does not mean that every gram of mass in the universe is simply Higgs mass. The distinction becomes obvious when we look at ordinary matter. Most of the mass of a chair, a mountain, a planet, or a human body is concentrated in atomic nuclei. Those nuclei are made from protons and neutrons, and most of the mass of a proton or neutron does not come from adding together the intrinsic Higgs-generated masses of the quarks inside it. Instead, the majority emerges from the energy of the strong interaction. Quarks move at relativistic speeds inside these particles. Gluon fields carry enormous amounts of energy. Quarks and gluons interact continuously through quantum chromodynamics, creating a bound quantum system whose total mass is far greater than the simple sum of the light quark masses. So the Higgs discovery answered one enormously important question while leaving another equally fascinating part of the mass puzzle in place. It showed that the Higgs field is not merely an attractive mathematical trick. Nature possesses the excitation predicted by that theory, with properties remarkably close to those required by the standard model. But the discovery also reminds us that mass has more than one quantum origin. The Higgs field explains the intrinsic masses of elementary particles. The heavier world of protons and neutrons tells a different story. And because those protons and neutrons account for almost all the mass of ordinary visible matter, the largest part of the answer is found not in the Higgs field alone, but deep inside the restless quantum interior of the proton. For a long time, the proton seemed like one of the simplest building blocks in nature. It carries one positive unit of electric charge. It sits inside atomic nuclei. Together with neutrons, it accounts for nearly all the mass of ordinary atoms. But the deeper physicists looked, the less simple the proton became. In 1964, Murray Gell-Mann and George Swake independently proposed that many particles then known as hadrons could be understood as combinations of more fundamental constituents. Gell-Mann called these constituents quarks. The word was unusual, and the particles themselves turned out to be even more so. According to the modern standard model, a proton is a type of hadron called a baryon. Its overall quantum numbers correspond to 2 up valence quarks and 1 down valence quark. A neutron has the opposite balance, with 1 up valence quark and 2 down valence quarks. This simple 3-quark description is extremely useful. It explains the proton's electric charge because each up quark carries positive 2/3 of the elementary electric charge. while a down quark carries negative 1/3. 2 up quarks and 1 down quark therefore produce a total charge of +1. But if we imagine 3 tiny quarks sitting motionless inside a hollow proton, like peas inside a pod, we have already wandered far away from the real quantum picture. A proton has no rigid outer shell. It is not a miniature container with a hard surface and 3 particles rattling around inside. Instead, it is a confined quantum state involving quark fields and gluon fields, all interacting through the strong force. The 3 valence quarks describe important persistent quantum properties of the proton, but they are not the whole contents of the particle. Inside the proton, gluons are constantly participating in the dynamics. Gluons are the quantum particles associated with the strong interaction. They carry energy and momentum, and because gluons themselves carry the strong interaction's color charge, they can interact directly with one another. This immediately makes the proton much more complicated than something like a simple 3-body planetary system. There are also contributions from what physicists call C-quarks. Quantum processes involving gluon fields can produce temporary quark and antiquark contributions within the proton's continuously changing internal state. These should not be imagined as little particles repeatedly popping into existence from literal nothingness. They are part of the full quantum description of the interacting fields inside the proton. At any moment, the proton structure reflects a restless mixture of valence quark contributions, C-quark and antiquark contributions, gluons, and the energy stored in their interactions. Experimental evidence for this internal structure became especially convincing through deep inelastic scattering. During the 1960s and early 1970s, experiments at the Stanford Linear Accelerator Center fired high-energy electrons at protons. Jerome Isaac Friedman, Henry Way Kendall, and Richard Edward Taylor played central roles in this work. If the proton had behaved like a smooth, featureless cloud of positive charge, the electrons would have scattered in one characteristic way. Instead, the scattering patterns suggested that electrons were striking compact, point-like constituents inside the proton. These constituents were initially described as partons. The results became powerful evidence that quarks were physically meaningful components of the proton rather than merely convenient mathematical bookkeeping. Later experiments revealed the essential role of gluons as well. Yet even the phrase inside the proton needs some care. A proton has a characteristic charge radius of roughly 8/10 of a femtometer. A femtometer is 1/quadrillionth of a meter. So the proton is unimaginably small by everyday standards. But this radius does not mark the position of a hard boundary. It describes how properties such as electric charge are distributed across the quantum state. There is no tiny spherical wall holding the quarks prisoner. And the quarks themselves are not quietly resting near the center. They are highly relativistic. This means their motion is energetic enough that the rules of special relativity are essential to describing them. Their kinetic energies are not small corrections that can be politely added after we have finished calculating the rest of the proton. They are a major part of the system. The gluon fields are equally important. Energy is continually stored and redistributed through the strong interaction. This is precisely where the proton's mass becomes so revealing. The proton has a rest energy of roughly 938 million electron volts, but the intrinsic mass parameters associated with the 2 up quarks and 1 down quark are only a few million electron volts each at commonly quoted reference scales. Even allowing for the fact that quark masses require careful definitions, the comparison is unmistakable. If we simply added the intrinsic masses of the 3 valence quarks, we would account for only a small fraction of the proton's measured mass. The old instinct that the mass of a composite object must equal the masses of its ingredients added together fails dramatically. The proton is far heavier than that simple sum. The reason is that a proton is not merely a bag containing three preformed massive objects. It is an entire interacting quantum system. Its total rest energy includes the relativistic motion of quarks, the energy of gluon fields, and the energy associated with the strong interaction binding the system into a stable hadron. Through Albert Einstein's relationship between mass and energy, that internal energy contributes directly to the invariant mass of the proton. This changes the original question in an important way. Asking what a proton is made of remains useful. It tells us about quarks and gluons. But if we want to understand why the proton has the mass it does, knowing the names of its constituents is not enough. We also need to know how those constituents behave. We need to understand the fields they belong to, the energy they carry, the way they interact, and why they remain confined within a system only a tiny fraction of the width of an atom. The proton is therefore a particularly beautiful example of emergent mass. Most of its mass is not sitting inside the quarks as a pre-existing ingredient. It arises from the energy of the quantum state formed by those quarks and gluons together. And once we look at the proton in that way, the deepest part of the question about ordinary mass becomes clearer. The answer is not hidden in a smaller object waiting to be discovered. It is hidden in the dynamics of the strong interaction itself. To understand why protons and neutrons have so much mass, we need to look more closely at the force responsible for holding their internal structure together. That force is the strong interaction. Its modern description is called quantum chromodynamics, the quantum field theory governing quarks and gluons. Quantum chromodynamics does for the strong interaction something broadly similar to what quantum electrodynamics does for electromagnetism. It describes matter fields, force-carrying fields, and the rules governing how they interact. But the strong interaction has some unusual features that make it very different from electromagnetism. The most important of these begins with something called color charge. Color charge has nothing to do with ordinary visible color. Quarks are not literally red, green, or blue. Those names are simply labels physicists use for three varieties of strong interaction charge. In electromagnetism, particles can carry positive or negative electric charge. In quantum chromodynamics, quarks carry color charge. The mathematics is more complicated than having just two signs. 3 color states are required, and the allowed combinations determine how quarks can form larger particles. A proton, for example, forms an overall color neutral state. This does not mean that its quarks have somehow lost their individual color charges. Instead, their combined quantum state is arranged so that the proton as a whole carries no net color charge detectable at large distances. The particles associated with transmitting the strong interaction are gluons. Here the comparison with electromagnetism becomes especially interesting. A photon carries no electric charge. Because of this, photons do not normally interact directly with other photons through ordinary electromagnetism. Gluons are different. Gluons themselves carry color charge. That means one gluon can interact directly with another gluon. This self-interaction makes the strong force extraordinarily rich and complicated. The mathematical foundations for this kind of theory were developed in the 1950s by Chen-Ning Yang and Robert Lawrence Mills. They investigated what are now called non-abelian gauge theories. The phrase sounds formidable, but the essential idea is that the symmetry transformations involved do not combine as simply as those in ordinary electromagnetism. The order in which certain transformations are applied matters. This deeper mathematical structure allows the force carrying particles themselves to carry the charge associated with the force. That is exactly what happens with gluons. Quantum chromodynamics was later developed as the theory applying this gauge structure to the color charge of quarks. One of its strangest properties concerns how the strength of the strong interaction changes with distance and energy. Normally, we might expect a force to become simpler as particles get closer together. In quantum chromodynamics, something rather remarkable happens. At extremely short distances, or equivalently when quarks are probed at extremely high energies, their strong interaction becomes weaker. This phenomenon is called asymptotic freedom. David Jonathan Gross, Frank Anthony Wilczek, and Hugh David Politzer independently played central roles in discovering this behavior during the early 1970s. Their work showed that quarks can behave almost as though they are free when examined at sufficiently short distances. This helps explain the results of high-energy scattering experiments, where quarks inside protons appeared to act like relatively independent point-like constituents during very brief interactions. But the opposite happens as the distance increases. At the scale of a proton, the strong interaction becomes much stronger. Rather than fading away gently as quarks separate, the interaction becomes increasingly difficult to ignore. This behavior is closely connected with quark confinement. Under ordinary low-energy conditions, isolated quarks are not observed. You cannot simply pull one quark out of a proton, place it on a laboratory table, and examine it on its own. The more energy supplied in an attempt to separate quarks, the more energy can become stored in the strong interaction field between them. Eventually, enough energy may be present to create new quark and antiquark combinations, producing new hadrons rather than leaving behind a lonely free quark. So the strong interaction becomes weaker when quarks are extremely close together and stronger when they are pulled farther apart. This is almost the reverse of the intuitive picture we build from familiar forces, and it is essential to understanding mass. The gluons carrying the strong interaction are massless elementary particles within the standard model, yet the fact that individual gluons have zero rest mass does not prevent them from contributing to the mass of a proton. A gluon can still carry energy and momentum. Inside a proton, the gluon field is highly active. Gluons interact with quarks and with other gluons. Energy is stored throughout this complicated quantum system. The quarks themselves are also moving with relativistic energies. When the entire proton is considered as one confined system, all of this internal energy contributes to its invariant mass. This is one of the places where Albert Einstein's relationship between energy and mass becomes inseparable from quantum field theory. The proton does not weigh what it does because someone has added together three heavy quarks. Its light quarks account directly for only a relatively small portion of its mass. Most of the mass belongs to the energy of the interacting system. The same basic physics applies to the neutron and to many other hadrons. Quarks and gluons organize themselves into stable or temporary quantum states, and those states can possess large masses even when the intrinsic masses of some of their constituents are tiny or exactly zero. This is why the question of what mass is made from becomes slightly misleading at the quantum level. If we ask what a proton contains, the answer includes quarks and gluons. But if we ask why the proton has almost 1 billion electron volts of rest energy, the answer lies largely in what those quarks and gluons are doing. They move. They exchange gluons. The gluons interact with one another. Strong fields store energy. The entire confined quantum state contributes to the final mass. Quantum chromodynamics therefore provides the framework that allows relatively light ingredients to produce much heavier composite particles. Mass has not appeared from nowhere. The energy is part of the physical system itself. What looks from the outside like the simple mass of a proton is, on the inside, the quiet numerical result of an extraordinarily active world of quantum fields. If quarks are real constituents of protons and neutrons, a very natural question follows. Why can we not simply remove one? Physicists can knock electrons away from atoms. They can split nuclei apart. They can even destroy protons in sufficiently energetic collisions and study the particles produced afterward. Yet no experiment has ever produced a single isolated quark that then travels freely through a detector. This behavior is known as quark confinement. According to quantum chromodynamics, quarks and gluons are normally confined within particles called hadrons. Protons and neutrons are examples of hadrons, as are mesons and many other short-lived particles produced in high-energy collisions. The common feature is color neutrality. Quarks carry the strong interaction property called color charge, while observable hadrons arrange those color charges into combinations that are neutral overall. Under ordinary low-energy conditions, nature seems unwilling to provide us with a single exposed color charge. This is very different from electromagnetism. Imagine two particles carrying opposite electric charges. They attract each other, but as they are moved farther apart, the electromagnetic force between them becomes weaker. Given enough energy, there is nothing fundamentally preventing the charges from being separated by an enormous distance. Quarks behave differently. As two quarks are separated, the strong interaction does not simply fade away in the same manner. At sufficiently short distances, quarks interact comparatively weakly because of asymptotic freedom. But across the distances characteristic of hadrons, the interaction becomes much stronger. A useful approximate picture is that the strong color field becomes concentrated into a narrow region between separating quarks. This is often called a color flux tube. The image can resemble a stretched string connecting the quarks. As the quarks are pulled farther apart, energy accumulates in this strong field configuration. But the string comparison should be treated carefully. There is no ordinary material cord connecting two tiny objects. The color flux tube is a description of the behavior of strongly interacting quantum fields, and something remarkable happens if enough energy is added. Instead of eventually pulling one quark completely free, the stored energy can become sufficient to produce a new quark and antiquark pair. The original color connections can then reorganize. Rather than ending with one isolated quark on one side and another isolated quark somewhere else, the system produces new color neutral hadrons. The attempt to liberate a quark has created more particles instead. It is a little like pulling so hard on something that, instead of revealing a loose end, nature quietly provides two new ends and refuses to explain itself further. This behavior appears dramatically in high-energy particle collisions. When an energetic quark or gluon is produced in a collision, it cannot simply fly through a detector as an isolated colored particle. Instead, the energy associated with that quark or gluon develops into a cascade of additional quarks and gluons. These then reorganize into color-neutral hadrons. The process is called hadronization. The resulting particles often emerge in a narrow spray called a particle jet. Collider detectors therefore do not photograph an individual free quark. They record collections of hadrons whose energies and directions preserve information about the energetic quark or gluon that initiated the jet. This is one of the ways physicists study quarks and gluons despite never observing them as ordinary isolated low-energy particles. The theoretical understanding of confinement was greatly advanced by Kenneth Geddes Wilson. During the 1970s, Wilson developed lattice gauge theory, a way of studying gauge fields by representing space-time as a discrete grid rather than an infinitely continuous background. This approach became particularly important for quantum chromodynamics, because the strong interaction becomes difficult to calculate using ordinary perturbative techniques at the comparatively low energies found inside protons and neutrons. In this strongly coupled regime, the convenient assumption that interactions are merely small corrections no longer works. Lattice calculations allow physicists to investigate quantum chromodynamics numerically and provide powerful evidence for confinement and the spectrum of massive hadrons that emerge from the theory. There is an especially deep feature hidden in all of this. If we imagine an idealized version of quantum chromodynamics in which the quark masses are set to zero, the classical equations do not contain an obvious mass scale corresponding to the roughly billion electron-volt mass of a proton. Yet the quantum theory develops a characteristic energy scale through its own dynamics. The strength of the strong interaction changes with the energy at which it is examined. This running of the interaction introduces a physical scale into the quantum theory. At high energies, asymptotic freedom makes the interaction weak. At lower energies, the interaction becomes strong. Around the scale associated with hadrons, quantum chromodynamics produces confinement and massive bound states. So even a theory built partly from particles that are massless, or nearly massless, can generate a family of composite objects with substantial masses. This is not an extra material ingredient being inserted into the proton. It is an emergent property of the quantum fields and their interactions. Confinement provides the environment in which this energy remains organized. The quarks inside a proton cannot simply drift away carrying their small intrinsic masses with them. Their motion is inseparable from the gluon fields and strong interactions forming the complete proton state. The energy stored in those fields, the relativistic motion of the quarks, and the continual strong interaction among quarks and gluons all belong to the same confined system. That system has a definite total rest energy, and therefore it has mass. This is why confinement matters so much when we ask what ordinary mass is actually made from. It ensures that the enormous internal energies generated by quantum chromodynamics are not merely temporary additions surrounding otherwise simple quarks. They are part of the stable structure of protons and neutrons themselves. A proton remains a proton because its quark and gluon fields occupy a particular confined quantum state. And when we measure the proton's mass, we are measuring the energy of that whole state. The quarks do not need to be individually heavy. The system they form is. A proton has a rest energy of roughly 938 million electron volts. That number is familiar enough in particle physics, but it becomes rather puzzling when we compare it with the particles we normally say the proton contains. A proton has the quantum numbers associated with 2 up valence quarks and 1 down valence quark, yet the intrinsic masses assigned to the up and down quarks are only a few million electron volts each at commonly used reference scales. Adding those 3 light quark masses together, therefore, gets us nowhere close to the measured mass of the proton. The missing mass is not evidence for some undiscovered pile of heavy material hiding inside it. Instead, most of the proton's mass belongs to the energy of the strongly interacting quantum system itself. The quarks are highly relativistic. Their motion contributes energy. Gluon fields carry energy and momentum. Quarks interact with gluons, gluons interact with other gluons, and additional quark and antiquark contributions appear within the complete quantum state. All of these ingredients are governed by quantum chromodynamics, and when the energy of that complete confined state is measured in the proton's rest frame, it corresponds to the proton's mass. This is sometimes described by saying that the proton's mass comes from binding energy. There is a useful idea hiding in that phrase, but it can also be misleading. In a familiar bound system, binding often reduces mass. If separate protons and neutrons combine into an atomic nucleus and release energy, the resulting nucleus has slightly less mass than its separated ingredients. The escaped energy is no longer contained within the system. A proton is not quite like this. Its constituent-like quarks do not begin with masses remotely close to the proton's final mass and then merely lose a little energy when they bind together. Instead, the strong interaction generates the dominant energy scale of the entire hadron. So it is better to think of the proton as a dynamical quantum object whose mass emerges from the behavior of its quark and gluon fields. There is an especially remarkable reason quantum chromodynamics can do this. In an idealized version of the theory in which quark masses are taken to zero, the classical equations possess no obvious built-in mass scale corresponding to the proton's roughly billion electron-volt rest energy. Yet the quantum theory creates a characteristic scale. This process is known as dimensional transmutation. The strength of the strong interaction is not fixed at one value. It changes according to the energy scale at which the interaction is examined. At very high energies, the interaction becomes weak through asymptotic freedom. At lower energies, around the scale of protons and other hadrons, it becomes strong. Through quantum effects. This changing interaction strength introduces a physical energy scale into a theory that, in its idealized classical massless form, did not contain one of the same kind. That dynamically generated scale is intimately connected with why strongly interacting particles such as protons and neutrons are massive. Another part of this story appears in something called the quantum chromodynamic trace anomaly. The name sounds rather ominous, but an anomaly in quantum field theory does not necessarily mean that the theory has made a mistake. It can mean that a symmetry present in the classical version of a theory does not survive unchanged after quantum effects are included. For idealized quantum chromodynamics with massless quarks, the classical theory has a form of scale symmetry. Roughly speaking, there is no preferred built-in length or mass scale. Quantum effects break that classical scale symmetry. This breaking appears mathematically in the trace of the energy-momentum tensor, the object physicists use to describe the distribution and flow of energy and momentum in a field theory. The resulting trace anomaly is closely related to the emergence of the quantum chromodynamic mass scale, and therefore to the existence of massive hadrons even when the light quark masses are imagined to vanish. Physicist Shandong Ji developed an influential way of examining the proton's mass by decomposing its energy into contributions associated with quark energies, gluon energies, explicit quark masses, and the quantum effects connected with the trace anomaly. This provides a useful way to ask how different aspects of quantum chromodynamics participate in the proton's total mass, but the numbers obtained from such decompositions require care. There is not always one unique way of slicing the proton's mass into separate pieces and then treating every piece as though it were an independently stored substance. Precise partitions can depend on how quantities are defined, on the renormalization scale being used, and on the theoretical scheme used to separate different contributions. That is why simple statements such as most of the proton is just gluon energy can conceal important subtleties. Gluons are enormously important, but the proton is a coupled quark and gluon system. Quark motion, gluon field energy, quark-gluon interactions, explicit quark masses, and quantum anomalous effects are not a collection of little substances sitting in separate compartments. They are different aspects of one interacting quantum state. Modern treatments of proton mass decomposition continue to examine precisely how those contributions should be defined and interpreted. The safest high-level conclusion is also the most striking one. Only a comparatively small part of the proton's mass is directly associated with the intrinsic masses of its light quarks. The overwhelming majority emerges from quantum chromodynamics itself. In other words, if the light quarks were imagined to become much lighter, the proton would not simply shrink towards zero mass with them. The strong interaction still generates a substantial hadronic energy scale. This makes the proton perhaps the clearest everyday example of emergent mass. Nearly every ordinary object around us contains enormous numbers of protons and neutrons. Most of the mass of those nucleons does not exist as tiny packets already stored inside their elementary constituents. It belongs to the restless quantum system those constituents create together. So when we ask what the mass of a proton is really made from, there is no smaller lump of mass waiting at the bottom. There are quark fields and gluon fields, confined together by the strong interaction. There is motion. There is field energy. There are quantum interactions and quantum effects that generate their own characteristic scale. And when all of that energy is gathered into one stable proton and viewed in its rest frame, nature gives that entire quantum state a mass of roughly 938 million electron volts. Knowing that most of a proton's mass emerges from quantum chromodynamics is one thing. Actually calculating that mass is another. The difficulty comes from the unusual behavior of the strong interaction. At very high energies, quarks interact comparatively weakly, and physicists can often use approximation methods that treat complicated interactions as a series of increasingly small corrections. Inside a proton, however, the strong interaction is strong. The quarks and gluons are so deeply coupled that the usual approximation techniques become unreliable. There is no simple picture in which three nearly independent quarks sit inside the proton while a few small corrections are added afterward. Everything is interacting with everything else. To deal with this regime, physicists use a method called lattice quantum chromodynamics. The basic idea is surprisingly visual. Ordinary quantum field theory treats space and time as continuous. There is no smallest mathematical gap between one position and the next. In lattice quantum chromodynamics, physicists temporarily replace that continuous spacetime with a grid. Imagine an enormous four-dimensional network of closely spaced points, with 3 dimensions representing space and another representing time. Quark fields are represented on this lattice, while the gluon fields responsible for the strong interaction are encoded in connections between neighbouring points. The lattice is not assumed to be a real microscopic grid built into the universe. It is a computational tool. As the spacing between lattice points is made smaller and the simulated region is made sufficiently large, physicists can work toward the behaviour expected in continuous spacetime. One of the central figures in developing this approach was Kenneth Geddes Wilson. During the 1970s, Wilson formulated gauge theories on a space-time lattice in a way that preserved the essential gauge structure of theories such as quantum chromodynamics. This was especially valuable because it allowed strongly coupled quantum fields to be investigated without relying on the same weak interaction approximations that work at very high energies. The underlying calculation begins with quantum chromodynamics itself. Physicists specify quantities such as the quark masses and the strength of the strong interaction according to a chosen theoretical framework and reference scale. They then ask what kinds of composite quantum states emerge from those ingredients. The proton mass is not simply inserted into the calculation as the answer. Instead, the equations are used to determine how quarks and gluons behave together and what energies belong to the stable or relatively long-lived hadrons produced by the theory. That distinction is crucial. The light quark masses are inputs. The strong interaction is an input. The proton is an output of the interacting quantum theory. Of course, saying this is much easier than doing it. A quantum field can occupy an enormous range of possible configurations. On the lattice, physicists must account statistically for vast numbers of possible arrangements of quark and gluon fields. Modern calculations therefore rely on powerful supercomputers. The computer does not simply draw one proton and watch it evolve. Instead, numerical algorithms generate representative collections of possible field configurations, weighted according to the rules of quantum chromodynamics. From the statistical behavior of these configurations, physicists calculate correlation functions. Those correlations contain information about the particles the theory can produce. By examining how particular correlations change across the lattice, researchers can extract the energies associated with states having the quantum properties of protons, neutrons, mesons, and other hadrons. From those energies, their masses can be determined. The remarkable result is that the masses produced by lattice quantum chromodynamics agree closely with the observed spectrum of strongly interacting particles. Protons emerge with masses near their measured values. Neutrons do as well. So do many mesons and other hadrons. This is enormously important, because it shows quantitatively that quantum chromodynamics contains the physics necessary to generate the massive particles that dominate ordinary nuclear matter. The proton's nearly 1 billion electron volts of rest energy does not have to be hidden inside 3 enormously massive quarks. The simulation begins with light quark masses and the strong interaction, then allows the full quark and gluon dynamics to determine the energy of the resulting bound state. Most of the proton mass emerges from those dynamics. There is still experimental input involved. The quark masses must be determined from measurements, and the overall scale associated with the strong interaction must ultimately be connected with measured quantities. Lattice quantum chromodynamics is therefore not a calculation performed in complete isolation from experiment. But once the necessary fundamental parameters are fixed, the theory can predict a wide range of additional quantities. That predictive power is what makes the agreement so impressive. It is also why lattice calculations have become one of the strongest pieces of evidence supporting the modern explanation of ordinary mass. The calculations are demanding. If the lattice spacing is too large, important short-distance behavior can be distorted. If the simulated volume is too small, the finite boundaries can affect the result. And realistic up and down quarks are extremely light compared with the characteristic strong interaction scale, which historically made simulations with physical light quark masses particularly expensive. Researchers therefore have to control several sources of error. They perform calculations at different lattice spacings, different simulated volumes, and increasingly realistic quark masses, then carefully extrapolate toward the physical limit. As computing power and algorithms have improved, these calculations have become substantially more precise. The result is something rather extraordinary. A question that sounds almost philosophical can be turned into a numerical experiment. We can ask why a proton weighs what it does. We can write down the quantum theory of quarks and gluons. We can represent that theory on a lattice, simulate its strongly interacting fields, and calculate the energy of the proton state that emerges. And the answer comes out close to the proton measured in laboratories. That is a profound confirmation of the idea that most ordinary mass is emergent. The mass of the proton is not merely assigned to it because experiments say it should have one. It arises from the dynamics of quantum chromodynamics. A restless collection of light quark fields and massless gluon fields, confined and interacting through the strong force, produces a stable quantum object with nearly 1 billion electron volts of rest energy. And because protons and neutrons make up nearly all the mass of ordinary atoms, lattice quantum chromodynamics allows us, in a very real sense, to calculate where much of the visible mass around us comes from. Protons and neutrons are remarkably similar particles. Both are built from 3 valence quarks. Both are held together by the strong interaction. Both have masses corresponding to just under 1 billion electron volts. And inside atomic nuclei, they behave in many ways like close relatives. But they are not quite identical. A neutron is slightly heavier than a proton. The difference is only about 1.3 million electron volts. Compared with the total mass of either particle, that is tiny. The proton has a rest energy of roughly 938 million electron volts, while the neutron is a little above 939 million electron volts. So the difference is only around 1 part in 700. And yet that small difference has enormous consequences. To understand where it comes from, we need to look again at the quark content of the 2 particles. A proton has 2 up valence quarks and 1 down valence quark. A neutron has 1 up valence quark and 2 down valence quarks. The important detail is that the down quark is intrinsically heavier than the up quark. Both of these light quarks acquire their intrinsic masses through their interactions with the Higgs field. But the strengths of those interactions are different. The down quark couples more strongly to the Higgs field than the up quark does, giving it the larger intrinsic mass. So at first glance, the neutron seems easy to explain. It contains 2 down quarks rather than 1. Because down quarks are heavier, the neutron should be heavier. And broadly speaking, that is indeed part of the answer. But there is another effect pulling in the opposite direction. The proton carries positive electric charge. The neutron is electrically neutral overall. Because the proton is charged, its internal electric charge distribution produces electromagnetic field energy. That electromagnetic contribution tends to increase the proton's mass relative to the neutron. So we have 2 competing effects. The difference between the intrinsic masses of the up and down quarks tends to make the neutron heavier. Electromagnetic effects tend to make the proton heavier. Nature settles on the small difference remaining after both contributions are taken into account. The quark mass effect wins. The neutron therefore ends up heavier by roughly 1.3 million electron volts. This is another example of why the mass of a composite quantum object cannot simply be found by adding together a few constituent particle masses. The proton and neutron are strongly interacting systems. Their masses are dominated by quantum chromodynamics, including quark motion, gluon fields, and strong interaction dynamics. The small difference between them then depends on more delicate effects layered on top of this enormous shared mass. One of those effects comes from the difference between the up and down quark masses. Another comes from electromagnetism. Separating these contributions accurately is difficult because the strong interaction is already highly non-perturbative at the scale of protons and neutrons. This is where lattice calculations become extremely useful. The Budapest-Marseille-Wuppertal lattice collaboration has carried out high-precision numerical calculations incorporating both quantum chromodynamics and electromagnetic effects. By simulating quarks, gluons, and electromagnetic interactions together, researchers have been able to reproduce the small mass differences between closely related hadrons, including the neutron and proton. This is an impressive achievement. The calculation is not merely trying to explain why both particles have masses near 1 billion electron volts. It is sensitive enough to reproduce a difference of only around 1 million electron volts sitting on top of that much larger scale. And that tiny difference matters far beyond particle physics. Because the neutron is heavier than the proton, an isolated neutron is unstable. A free neutron can undergo beta decay. during this process. One of the neutron's down quarks is transformed into an up quark through the weak interaction. The neutron becomes a proton, while an electron and an electron antineutrino are also produced. A free neutron survives on average for only around 15 minutes before decaying. Inside a stable atomic nucleus, however, the situation can be different. Nuclear binding energy changes the total energy balance, and many neutrons can remain stable indefinitely when bound within suitable nuclei. The proton occupies a particularly important position. Because it is lighter than the neutron and is the lightest baryon, there is no lighter baryonic state into which an isolated proton can simply decay while conserving the required quantum properties. Within the standard model, the proton is therefore stable against ordinary particle decays. Experimentally, no proton decay has ever been observed. This small ordering of masses is profoundly important for the structure of the universe. Ordinary hydrogen consists of a single proton with an electron bound to it, if the proton were heavier than the neutron by the wrong amount. Hydrogen could become unstable through processes that would transform protons into neutrons. The simplest and most abundant atom in the universe might not survive in anything like its familiar form. That would alter the entire path of cosmic history. Hydrogen fuels stars. Stars build heavier elements. Those elements form planets, molecules, oceans, atmospheres, and living organisms. The tiny neutron-proton mass difference therefore sits near the foundation of an enormous chain of physical consequences, and it depends partly on the Higgs field. The difference between the up and down quark masses originates in their different Higgs interactions, but it also depends on electromagnetic energy and the complicated strong interaction environment inside the nucleons. Once again, no single mechanism owns the whole story. Most of the proton and neutron masses come from quantum chromodynamic dynamics. The slight difference between them reflects the unequal intrinsic masses of the up and down quarks, combined with electromagnetic corrections. A change of only a little over 1 million electron volts is enough to decide which particle is heavier. And from that very small quantum imbalance comes the stability of hydrogen, the behavior of nuclei, the fuel of stars, and much of the familiar structure of matter around us. Once protons and neutrons exist, the story of mass is still not quite finished. Those particles can combine to form atomic nuclei, and when they do, the mass of the finished nucleus is not simply the total mass of all the individual protons and neutrons added together. Something changes. The reason is nuclear binding energy. Protons and neutrons, which are collectively called nucleons, interact through what is known as the residual strong nuclear interaction. This force is related to the much deeper strong interaction described by quantum chromodynamics, but it acts between already formed protons and neutrons rather than directly between isolated quarks. A useful comparison is the difference between electromagnetism inside an atom and the weaker forces that can act between complete atoms and molecules. The underlying physics is connected, but the effective interaction appears at a different level. Inside an atomic nucleus, the residual strong interaction can attract nearby protons and neutrons strongly enough to hold them together. This is particularly important for protons because they also repel one another electrically. Every proton carries positive electric charge. Bring two protons close together and the electromagnetic interaction tries to push them apart. The nuclear force therefore has to compete with this repulsion. At the very short distances typical of atomic nuclei, the attractive nuclear interaction can dominate and allow stable nuclei to form. But forming a stable bound nucleus changes the total energy of the system. Imagine beginning with several isolated protons and neutrons separated far enough apart that they are not bound together. If those nucleons come together into a more stable nuclear configuration, energy is released. That energy might eventually appear as electromagnetic radiation, kinetic energy, or other forms of energy carried away from the newly formed nucleus. Once the energy has escaped, the completed nucleus contains less total energy than the original separated nucleons did. And because total rest energy contributes to invariant mass, the bound nucleus has less mass. This difference is called the nuclear mass defect. The name can sound as though some material has gone missing, but nothing mysterious has disappeared. The lower mass simply reflects the lower energy of the bound system. The relationship can be expressed through Albert Einstein's mass-energy principle. In spoken form, the released binding energy equals the missing mass multiplied by the speed of light multiplied by the speed of light. Because the speed of light is so large, a very small change in mass can correspond to a considerable amount of energy. Evidence for these tiny differences in atomic and nuclear masses began to emerge clearly through increasingly precise measurements during the early 20th century. Francis William Aston played an important role in this work. Using mass spectrometry, Aston measured the masses of isotopes with far greater precision than had previously been possible. His results showed that atomic masses did not behave as though nuclei were assembled from perfectly additive chunks with simple whole number masses. The deviations were physically meaningful. They reflected the energies associated with nuclear structure and binding. The amount of binding varies from nucleus to nucleus. Physicists often compare nuclei using binding energy per nucleon, which measures roughly how tightly each proton or neutron is bound on average. Very light nuclei tend to become more tightly bound as additional nucleons are assembled into somewhat heavier nuclei. The binding energy per nucleon rises across much of the lighter part of the nuclear landscape. Eventually it reaches a broad maximum among medium mass nuclei, particularly around iron and nickel. These nuclei are among the most tightly bound arrangements of protons and neutrons in nature. Beyond this region, the average binding per nucleon gradually decreases for very heavy nuclei. This pattern explains why two apparently opposite nuclear processes can both release energy. Light nuclei can release energy through nuclear fusion. When small nuclei combine to form a more tightly bound larger nucleus, the final system has slightly less mass than the original components. The missing rest mass appears as other forms of energy. Very heavy nuclei can release energy through nuclear fission. If a heavy nucleus divides into medium-sized fragments that are more tightly bound per nucleon, the products can again have a lower total mass than the original nucleus. The difference emerges as released energy. Stars provide the most familiar large-scale example of nuclear mass changing through binding. Inside the Sun, hydrogen nuclei ultimately participate in reactions that produce helium. The final helium nucleus has a lower mass than the combined mass of the original particles that eventually contributed to it. Roughly 0.7% of the mass involved in converting hydrogen into helium is released in other forms of energy. That fraction may sound small, but on the scale of the Sun it is enormous. Every second the Sun converts hundreds of millions of tons of hydrogen into helium. A few million tons of equivalent mass are transformed into energy each second, ultimately emerging as radiation, particle motion, and neutrinos. Some of that radiation eventually reaches Earth as sunlight. So the warmth of sunshine is connected, in part, with an extremely small reduction in the mass of bound nuclear systems. But this should not be confused with the much larger origin of the proton and neutron masses themselves. A proton already possesses nearly all of its mass before it becomes part of a nucleus. That mass comes predominantly from the energy of its internal quark and gluon fields governed by quantum chromodynamics. Nuclear binding then makes a smaller adjustment. When protons and neutrons settle into a bound nucleus, the negative binding energy reduces the total mass of the finished nucleus compared with the separated nucleons. So the hierarchy is important. First, strong interaction dynamics inside protons and neutrons generate most of the mass of ordinary matter. Then the residual nuclear interaction rearranges those already massive nucleons into nuclei and changes the total mass slightly through binding energy. The same principle will appear again at still larger scales. Electrons bind to nuclei. Atoms form molecules. Molecules form solids, liquids, living cells, mountains, and planets. Every time a system gains or loses internal energy, its total mass changes in principle. Usually the change is far too small to notice without exceptionally precise instruments. But the effect is real. Mass is therefore not merely something that survives unchanged as matter is assembled into larger structures. It keeps track of the total energy of those structures. A bound nucleus weighs slightly less than its separated parts because it contains less energy. And in stars, laboratories, nuclear reactors, and radioactive nuclei, those tiny mass differences can become some of the most powerful energy releases in the physical universe. Once protons and neutrons are assembled into nuclei, the mass of the world around us begins to take on a more familiar shape. Atoms form. Molecules appear. Solids, liquids, gases, rocks, oceans, living cells, and entire planets can eventually be built from the same small collection of quantum ingredients. But even at these larger scales, mass is still keeping track of something deeper than a simple count of particles. Consider an ordinary atom. Almost all of its mass is concentrated in the nucleus. The electrons surrounding that nucleus are essential for chemistry, electrical behavior, and the structure of matter, but they contribute comparatively little to the total mass. A proton is roughly 1,830, 6 times more massive than an electron. A neutron is slightly heavier than a proton. So even in an atom containing many electrons, the overwhelming majority of the mass is normally found in the protons and neutrons packed into the nucleus. Hydrogen gives us the simplest example. The most common form of hydrogen contains 1 proton in its nucleus and 1 electron surrounding it. The proton accounts for almost all the atom's mass. The electron is crucial to everything hydrogen does chemically, but numerically its contribution to the mass is tiny. Heavier atoms contain larger nuclei. Helium usually contains 2 protons and 2 neutrons. Carbon commonly contains 6 protons and 6 neutrons. Oxygen commonly contains 8 protons and 8 neutrons. As nuclei grow, more of the atom's mass is concentrated in these collections of nucleons. But even here, adding together the masses of separate protons and neutrons does not give exactly the mass of the finished nucleus. Nuclear binding energy changes the total. When nucleons bind into a stable nucleus and energy is released, the bound nucleus ends up slightly lighter than the same protons and neutrons would be if they were separated. So the mass of an atom already contains several layers. Most of the mass of each proton and neutron comes from strong interaction dynamics involving quarks and gluons. The intrinsic masses of the light quarks contribute a smaller amount. Nuclear binding then reduces the combined mass slightly, and after that, the electrons add their own small masses. There is still another adjustment. Electrons are not simply parked motionless around the nucleus. They occupy quantum states determined largely by the electromagnetic interaction between their negative electric charge and the positive charge of the nucleus. When an electron becomes bound to an atomic nucleus, the energy of the complete atom is slightly lower than the energy of the same nucleus and electron when separated. That difference is atomic binding energy. Once again, a lower total energy means a slightly lower total mass. The effect is much smaller than nuclear binding energy. Typical atomic electron binding energies are measured on scales of electron volts, while nuclear binding energies are commonly measured in millions of electron volts. And the rest energies of protons and neutrons are close to 1 billion electron volts each. So there is a very clear hierarchy. Strong interaction dynamics dominate the mass of individual nucleons. Nuclear binding shifts the masses of nuclei by a smaller amount. Atomic electromagnetic binding changes them by a smaller amount again. But every one of these effects is real. If measurements are precise enough, the tiny mass differences associated with atomic binding can be detected. The same principle continues when atoms form molecules. Imagine two atoms approaching one another and forming a chemical bond. If the resulting molecule is more stable than the separated atoms, energy is released during the bonding process. That energy might leave as radiation, vibrations, collisions with surrounding particles, or heat. Once the released energy has escaped, the final molecule has slightly less total mass than the isolated atoms had before bonding. The change is extraordinarily small. Chemical energies are tiny compared with nuclear energies. A household scale will never notice the mass difference created when chemical bonds form in an ordinary reaction. But in principle, the difference is there. Even familiar chemistry therefore obeys the same basic relationship between mass and energy. A battery that is fully charged has a minutely greater mass than the same battery after some of its stored energy has been released. A stretched spring has slightly more mass than the same spring when relaxed, provided the entire system is compared carefully. A hot sealed object has slightly more mass than the same object when cold. That last example can feel particularly strange. Heat seems almost weightless in everyday life. But heating a sealed object increases its internal energy. Atoms vibrate more strongly in a solid. Molecules move more energetically in a gas. Internal quantum states may become more populated. If none of that energy escapes, the total rest energy of the object increases, and so does its mass. The increase is far too small to notice with ordinary weighing equipment. Heating 1 kilogram of water by a modest amount might add only an unimaginably tiny fraction of a kilogram to its mass. Yet the principle is exact. Energy stored inside a system contributes to the invariant mass of that system. This allows us to trace the mass of an everyday object through several levels of physics. Take something simple, perhaps a stone resting on a table. The stone is built from molecules or extended crystal structures. Those are built from atoms. The atoms contain electrons and nuclei. The nuclei contain protons and neutrons. The protons and neutrons contain strongly interacting quark and gluon fields. At the deepest level relevant to most of the stone's mass, quantum chromodynamics is doing most of the work. The quarks themselves possess intrinsic masses through their interactions with the Higgs field. Those masses matter. Without them, the properties of protons, neutrons, nuclei, and the wider structure of matter would change. The electron mass also matters enormously. The size of atoms and the energies associated with chemical bonding depend strongly on the electron's mass. So it would be wrong to dismiss Higgs-generated masses simply because their direct contribution to the total weight of ordinary matter is small. They help determine what kinds of stable structures the universe can form. But if we ask where the numerical mass of a stone, a human body, an ocean, or a planet mostly resides, The answer points overwhelmingly toward atomic nuclei, and inside those nuclei, it points toward protons and neutrons, and inside protons and neutrons, it points toward the energy of quantum chromodynamics. This gives us a layered picture. The Higgs field helps establish the intrinsic masses of elementary particles. The strong interaction generates most of the mass of nucleons. Nuclear binding slightly reduces the mass when nucleons assemble into nuclei. Atomic binding adjusts it again when electrons settle around those nuclei. Chemical bonds alter it by still smaller amounts when atoms form molecules. Thermal energy can raise it slightly when an object is heated. Every level contributes to the total energy budget, and every contribution, however small, belongs to the final mass of the complete object. So a kilogram of ordinary matter is not a kilogram, because nature has hidden a kilogram of some fundamental mass substance inside it. Its mass is the combined result of quantum fields, particle properties, strong interaction dynamics, binding energies, motion, and stored internal energy. The solid and reassuring weight of everyday matter is therefore built from something surprisingly dynamic. What feels like a simple property of an object in your hand is, underneath, the accumulated result of several layers of quantum physics quietly working together. At first, the idea that massless particles can help form something massive sounds almost contradictory. If the ingredients have no rest mass, how can the finished system have any mass at all? The answer is found in the difference between the mass of an individual particle and the invariant mass of an entire system. Photons provide the clearest example. A photon has zero rest mass. It always travels through empty space at the speed of light, and there is no inertial frame in which a photon can simply be brought to rest. Yet photons carry energy. They also carry momentum. This means that a collection of photons can have a total energy and a total momentum, and from those two quantities, the invariant mass of the complete system can be determined. The important point is that the mass of the system does not have to equal the sum of the individual rest masses of the particles inside it. Imagine two photons travelling in exactly the same direction. Each photon has energy and momentum, and because they are moving together, their momenta point the same way. If we add the two photons together as one physical system, their total energy increases, but so does their total momentum. For two perfectly parallel photons, the relationship between the total energy and total momentum still corresponds to a system with zero invariant mass. Now change just one thing. Let the two photons travel in opposite directions. Suppose they have equal energies. Their individual momenta now point in opposite directions and cancel. The combined system has zero total momentum. But the photons still carry energy, so we now have a system that contains positive total energy while possessing no net momentum. That system has a non-zero invariant mass. Nothing has happened to the photons individually. Each one remains massless. The mass belongs to the two-photon system considered as a whole. This is one of the most useful examples for understanding why composite mass cannot be reduced to a simple inventory of constituent rest masses. Mass depends on the total energy and momentum structure of the complete system. The same idea can be made more concrete with a sealed box. Imagine a perfectly reflecting box with nothing inside it. Measure the mass of the box. Now place electromagnetic radiation inside and arrange things so that the light remains trapped, continually reflecting from the walls. The photons inside still have zero rest mass, but the box now contains additional energy. From the point of view of someone observing the complete box while it is at rest, the various photon momenta average together so that the total momentum of the enclosed system remains zero. The trapped radiation, therefore, adds to the rest energy of the entire box. The box with light inside is slightly more massive than the identical empty box. If the radiation escapes, the mass of the box decreases again. This is not a special loophole created for light. It is a general consequence of relativity. The total invariant mass of a closed system reflects its total energy measured in the frame where the system as a whole has zero momentum. This is why phrases such as energy has mass need to be used with some care. They point towards something real, but they can also create confusion. A single photon has energy, but it does not therefore possess a non-zero invariant rest mass. It is more accurate to say that energy contained within a system can contribute to the invariant mass of that system. The distinction becomes extremely important inside a proton. Gluons are massless elementary particles within the Standard Model. Yet gluons carry energy and momentum. They also interact strongly with quarks and with other gluons. Inside a proton, the gluon field forms part of a complicated, confined quantum state. There is no requirement that each gluon must possess an individual rest mass before its energy can contribute to the mass of the proton. The proton is not assembled by taking the rest masses of every quark and gluon and adding them together like numbers on a shopping receipt. Instead, the proton's mass belongs to the full interacting system. The quarks possess small intrinsic masses, the gluons are individually massless. But the quarks move with large relativistic energies. The gluon fields contain energy. Quarks and gluons continually exchange energy and momentum through the strong interaction. And because the proton is a confined system, all of these contributions combine into a stable state with a definite total rest energy. That total rest energy corresponds to the proton's invariant mass. The distinction between constituent mass and system mass, therefore, removes what otherwise looks like a paradox. A proton is heavy even though some of the fields contributing most strongly to its internal energy are associated with massless particles. There is no contradiction. The individual gluons do not need to be massive, because the proton's mass is not defined by asking how much rest mass each internal excitation possesses separately. It is defined by the energy and momentum of the entire bound quantum state. The same logic applies beyond particle physics. Any isolated system can, in principle, gain or lose mass when its internal energy changes. Heat contributes. Chemical energy contributes. Nuclear energy contributes. Radiation contributes. Internal motion contributes. The size of the effect depends on how much energy is involved, but the principle is universal. This is also why an excited atom has slightly more mass than the same atom in a lower energy state. If an electron occupies a higher atomic energy level, the atom contains more internal energy. When the electron falls to a lower level and a photon escapes, the atom loses that energy and its mass decreases by an extraordinarily tiny amount. Again, no individual constituent needs to change its fundamental rest mass. The state of the system has changed. This brings Albert Einstein's relativity and quantum field theory together in a particularly elegant way. Quantum field theory tells us what the internal ingredients are and how they interact. Relativity tells us how the complete system's energy and momentum determine its invariant mass. Neither picture is enough on its own if we want to understand the mass of something as complicated as a proton. Quantum physics tells us that the proton is an interacting state of quark and gluon fields. Special relativity tells us that the energy contained in that state contributes to its mass. Together they explain how light quarks and massless gluons can form a particle much heavier than the simple sum of the quark masses. So the question of what mass is made from becomes even more subtle. Mass is not a hidden substance stored inside every particle, and it is not always inherited directly from the rest masses of smaller ingredients. Sometimes it belongs to the arrangement itself. It can emerge from motion, interaction, confinement, and field energy. A system can therefore be massive even when some, or in special cases all, of its individual constituents are massless. The crucial quantity is not simply what the system contains. It is how much total energy the system possesses, how that energy is distributed, and what total momentum remains when the system is viewed as a whole. That is why massless photons can add mass to a sealed box. It is why massless gluons can help account for the mass of a proton. And it is why the mass of ordinary matter cannot be understood simply by searching for smaller and smaller particles that carry tiny pieces of weight inside them. Modern physics can explain an extraordinary amount about mass. It can describe how elementary particles such as electrons and quarks acquire intrinsic mass through their interactions with the Higgs field. It can explain why protons and neutrons are much heavier than the light quarks they contain. It can calculate how binding energy changes the mass of nuclei, atoms, and molecules. And it can connect all of this with the relationship between energy, momentum, and invariant mass. Yet the picture is not complete. The standard model of particle physics is one of the most successful scientific theories ever constructed, but it still contains important unanswered questions about mass. One of the clearest comes from neutrinos. Neutrinos are extraordinarily light elementary particles that interact only weakly with ordinary matter. Enormous numbers of them pass through the Earth, through buildings, and through our bodies with almost no effect at all. In the original minimal form of the standard model, neutrinos were treated as exactly massless. Experiments eventually showed that this cannot be correct. Neutrinos occur in three types, commonly called electron neutrinos, muon neutrinos, and tau neutrinos. As they travel, they can change from one type into another. This phenomenon is called neutrino oscillation. For oscillations to occur in the observed way, the neutrino states involved must have different masses. The absolute values of those masses remain very small, but at least some neutrinos must possess non-zero mass. Two major experimental programs were especially important in establishing this. The Super Kamiokande experiment in Japan studied neutrinos produced when cosmic rays strike Earth's atmosphere. Takaki Kajita and collaborators found that the number and behavior of muon neutrinos depended on the distance they had travelled, providing strong evidence that the neutrinos were changing type. The Sudbury Neutrino Observatory in Canada studied neutrinos arriving from the Sun. Arthur Bruce MacDonald and collaborators showed that the total number of solar neutrinos was consistent with theoretical expectations once neutrino flavor change was taken into account. Together, these results established that neutrino oscillations are real, and therefore that neutrinos cannot all be exactly massless. This was an important discovery because it showed directly that the simplest standard model was incomplete. But it did not immediately reveal where neutrino mass comes from. One possibility is that neutrinos acquire mass in a broadly similar way to other fermions through interactions with the Higgs field. In such a description, neutrinos would have what is called Dirac mass. This would require additional neutrino states beyond those appearing in the original minimal standard model, often described as right-handed neutrinos. Another possibility is more unusual. Neutrinos may be Majorana particles. A Majorana particle is its own antiparticle. If neutrinos have this property, their masses could arise through mechanisms very different from the ordinary Higgs interactions responsible for the masses of charged leptons and quarks. Experiments searching for processes such as neutrinoless double beta decay are designed in part to test whether neutrinos possess this Majorana character. So even though physicists know that neutrinos have mass, the fundamental origin of that mass remains uncertain. There is another mystery hidden in particles whose Higgs interactions are already much better established. The Standard Model explains how the electron, muon, tau lepton, and 6 quarks can acquire masses once their Yukawa couplings to the Higgs field are specified. But it does not explain why those coupling strengths have the values that they do. The electron is light. The muon is more than 200 times heavier. The tau lepton is heavier again. Among the quarks, the differences are even more dramatic. The up and down quarks have intrinsic masses of only a few million electron volts at commonly used reference scales, while the top quark has a mass of roughly 173 billion electron volts. All of these particles interact with the same Higgs field. What differs is the strength of each Yukawa interaction. The Standard Model takes those strengths as parameters measured from nature. It does not currently derive their pattern from a deeper established principle. So physics can explain the mechanism that converts a Yukawa interaction into a particle mass without explaining why nature chose this peculiar collection of coupling strengths in the first place. There is also a much larger mass mystery in the universe. Astronomical observations show that visible matter cannot account for all the gravitational effects seen in galaxies, galaxy clusters, gravitational lensing, and the large-scale structure of the cosmos. This unseen component is called dark matter. Dark matter appears to contribute substantially more matter to the universe than the familiar atoms made from protons, neutrons, and electrons. Yet its microscopic identity remains unknown. Physicists do not yet know whether dark matter consists of one type of particle, several types, or something more unusual. And without knowing what dark matter is, there is no confirmed explanation for how its mass is generated. It might involve the Higgs field. It might involve another field or mechanism entirely. At present, that remains an open experimental question. The Higgs field itself also creates a theoretical puzzle. The characteristic scale associated with electroweak physics is tiny compared with much larger scales associated with gravity and possible unification of the fundamental forces. Quantum corrections to the Higgs mass make physicists ask why the observed Higgs scale remains so much lower than these enormous energy scales without requiring an apparently delicate balance of parameters. This is commonly called the hierarchy problem. Many theoretical ideas have been proposed to address it, including new symmetries, additional particles, composite Higgs models, and other extensions of known physics. None has yet been established experimentally as the correct solution, and beyond all of these questions lies gravity. The Standard Model is a quantum theory. Albert Einstein's general theory of relativity describes gravity and spacetime with extraordinary success. But physicists still do not possess a complete, experimentally confirmed theory that unifies general relativity with quantum physics. A successful theory of quantum gravity might eventually change or deepen our understanding of mass, energy, spacetime, and the structure of matter at the most fundamental level. For now, these two great frameworks remain incomplete when pushed together under the most extreme conditions, and yet it is worth noticing how much is already understood. The unanswered questions do not erase the enormous success of the existing picture. The intrinsic masses of known charged elementary fermions are connected with the Higgs field. The masses of the weak interaction bosons emerge through electroweak symmetry breaking. Most of the mass of protons and neutrons arises from quantum chromodynamic dynamics involving quark and gluon fields. Nuclear, atomic, and chemical binding energies then modify the masses of increasingly large composite systems. So physics has moved far beyond simply saying that objects possess mass, because that is one of their basic properties. It can trace much of ordinary mass into the behavior of quantum fields. But it cannot yet explain why every fundamental mass scale has the value that it does. It cannot yet say with certainty how neutrinos acquire their tiny masses. It cannot identify the particles responsible for dark matter. It cannot derive the full pattern of Yukawa couplings from a deeper confirmed theory. And it cannot yet place the standard model and gravity inside one experimentally tested quantum framework. The story of mass is therefore both remarkably successful and unfinished. For ordinary visible matter, we understand a great deal about where mass comes from. For the deeper pattern behind all masses in nature, there are still questions waiting quietly at the edge of the standard model. After following mass all the way down from everyday objects to atoms, nuclei, protons, neutrons, quarks, gluons, and quantum fields, the answer turns out to be both simpler and stranger than it first appears. Mass is not made from a special substance. There is no smallest grain of mass hidden inside matter, waiting to be uncovered beneath the quarks. Mass is a physical property of particles and systems, and its value can arise in different ways depending on what kind of object we are talking about. In classical mechanics, Isaac Newton treated mass as a fundamental measure of how strongly an object resists acceleration and how it participates in gravity. Albert Einstein then showed that the picture was deeper. In special relativity, invariant mass is tied to the total energy and momentum of a physical system. An object can contain internal energy, motion, radiation, and interactions, and all of these can contribute to the mass of the complete system. Quantum physics adds another layer by replacing the old picture of tiny solid particles with quantum fields. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons belong to the electromagnetic field. Gluons belong to the fields of the strong interaction. And the Higgs field fills the vacuum with a non-zero background value, but plays a central role in determining the intrinsic masses of several elementary particles. The Higgs field is important enough that it is sometimes described as the source of mass itself. That statement is useful only if we immediately add a large footnote. Interactions with the Higgs field do account for the intrinsic masses of known massive quarks and charged leptons, including the electron. The same field is also responsible for electroweak symmetry breaking, and helps explain why the W and Z bosons are massive, while the photon remains massless. The discovery of the Higgs boson at the European Organisation for Nuclear Research provided powerful experimental confirmation that this part of the standard model reflects something real in nature. But the Higgs field does not directly account for most of the mass of the ordinary matter around us. That part of the story belongs mainly to protons and neutrons. A proton has a rest energy of roughly 938 million electron volts. Yet the intrinsic masses of the light up and down quarks associated with its valence structure add up to only a small fraction of that value. The rest is not missing. It is present as the energy of the quantum system itself. Inside the proton, quarks move relativistically. Gluon fields carry energy and momentum. Quarks interact with gluons, gluons interact with one another, and the entire state is confined by the strong interaction described by quantum chromodynamics. The characteristic mass scale of the proton emerges dynamically from this strongly interacting quantum system. The same basic physics applies to the neutron. So most of the mass in the nuclei of ordinary atoms comes not from heavy elementary ingredients, but from the energy stored in and generated by interacting quark and gluon fields. That is the decisive part of the answer, and then smaller adjustments are added on top. When protons and neutrons bind into atomic nuclei, nuclear binding energy reduces the mass slightly. When electrons bind to nuclei, electromagnetic binding changes the total mass by a much smaller amount. Chemical bonds change it again by an even tinier amount. Heating a sealed object raises its internal energy and therefore increases its mass by an almost unimaginably small amount. All of these effects follow the same general principle. The mass of a complete system depends on its total energy and momentum. This is why even massless particles can contribute to the mass of something larger. A photon has zero rest mass, but a collection of photons can form a system with non-zero invariant mass. Gluons are massless elementary particles, yet the energy of gluon fields contributes enormously to the mass of a proton. So adding up the rest masses of microscopic ingredients is not enough. The arrangement matters, the motion matters, the interactions matter, the field energy matters. If we trace the mass of an ordinary person, book, planet, or sleeping listener downward, most of it leads into atomic nuclei. Those nuclei lead to protons and neutrons. And those particles lead into a restless quantum world dominated by quarks, gluons, confinement, and the strong interaction. What feels perfectly solid at our scale is, at a deeper level, the mass of a dynamic quantum state. Even then, physics has not reached a final answer to every question. Neutrinos possess tiny masses whose underlying origin is still uncertain. The standard model does not explain why the Yukoa couplings of the quarks and charged leptons have the particular values that nature appears to have chosen. Dark matter clearly contributes gravitational mass throughout the universe, yet its microscopic identity remains unknown. The hierarchy associated with the Higgs scale remains a theoretical puzzle, and a complete experimentally confirmed theory of quantum gravity has yet to unite the quantum description of matter with gravitation. So the modern explanation of mass is extraordinarily successful without being complete. According to quantum physics, mass is not primarily a material substance from which everything else is built. It is a measurable property of quantum particles and systems. For elementary particles, some intrinsic masses are connected with interactions with the Higgs field. For ordinary visible matter, most of the mass comes from the rest energy of strongly interacting quark and gluon fields confined inside protons and neutrons, which means that the weight of the familiar world is not hiding inside some final microscopic lump of mass. Much of it comes from energy, motion, fields, and interaction. The solid mass of matter is, in a very real sense, the visible weight of an invisible quantum dance.